Hello everyone. So today I would like to discuss, to give lecture about um, control engineering in the topic chapter 3, modeling in the time domain. So my main reference is S.Nise control systems engineering. It can be from any edition, but I use here is the global editions. So what we're going to cover today is converting a transfer function to state space and converting a state space to transfer function. All right. So we have actually what we have done so far is we have learned how to model a system, right? Model a system using transfer functions. And in chapter 2 and in chapter 3, we learn how to model the systems using state space equations. So the next step is we need to know how to transform the system from transfer function to state space and also transform the state space to transfer function. Okay, so the first one is converting a transfer function to state space. So theoretically, in general form, consider that you have a differential equations, which is d to the power of n, which is the y is differentiated n times, okay, plus with some constants, times with the y differentiated n minus 1 and so forth until equals to a constant b naught times with u, which is the input. Okay, so the first steps is in the general form, the first steps is we define the variable. Okay, so in this case, we define that x1 is equals to y, the output, x2 is equals to, we differentiate the y over time, and x3, we double differentiate the y over time, and up to xn, which is xn is, we differentiate the y to the n minus 1. Okay, so what determine how many variables that we have here is based on n here. So the xn here determines the numbers of variables that we define. So the next steps is we differentiate the variables. So if you see here, from x1, you differentiate to x1 dot. So what it means is that the y will be differentiated to dy dt. So similarly, it goes for x2, x3, and x4. So the last part is x1 dot, we can see the relationship. What happens is that x1 dot here, it is equals to dy d2, which is dy d2 for the state variables is actually x2. So that's what happens here, right? So then for x2 dot, here, we differentiate it. Actually, we differentiate it so it becomes double differentiation of dy of y signal. So which is actually in the state variables form, it is x3. So that's how it comes to x3. Until the last part, we get the xn dot, which is equals to some general form here, which is we obtain it from the main equations. Okay, so let's look at examples so you can easily see what is actually happening. Okay, but before to that, then when we have that, when we are able to put it in the third steps, then we just transform it into a state space equations here. Okay, so let's look at example. So find the transfer function representation in phase variable form for the transfer function for the following transfer function, where you have CS over RS equals to 24 over s to the power of 3 plus 9s to the power of 2 plus 26s plus 24. So in a block diagram, this one will be, you have a transfer function, which is 24 over s to the power of 3 plus 9s to the power of 2 plus 26s plus 24. So there is an input to the transfer function, which is Rs, and an output, which is Cs. Okay. So what happens here, the first step is we cross multiply. So the output signal Cs is multiplied by s to the power of 3 and the input signal RS is multiplied by 24. So this is what happens here. So the next step is, what you can see here is we are moving towards transforming the CS into, which is the S domain, into time domain here. Okay, so what is the C triple dot means that because this is S to the power of 3, so you have C triple dot, which represented by triple differentiation of the C signal. So the C signal here is differentiated 3 times. All right. So 9 C dot is because of the C here. Okay. So 9 C dot is because of the C here, S to the power of 2. So is 9 C double dot and 26 C dot and 24C, which is equals to 24R. So this is our one steps towards transforming it into a time domain. So next is we define the state variable. Okay, so define the state variables. Okay, so here they define the state variables, 3 state variables, which is x1 equals to C, x2 equals to C dot, and x3 equals to C double dot. So the question is how many state variables that we need to define? Okay, so if you see here, we have the transfer function is s to the power of 3. So this one here, it defines 3 state variables. So 3 state variables, which is x1, x2, x3. All right. So the number of state variables that we define is we can determine by the highest power of the transfer function that we have. Okay, that the question gave. So the next step is we differentiate the state variables. Differentiate the state variables. So in this case, when you differentiate x1 dot, you will get C dot. So when you look at x2, it is actually equals to x2, right? So when you differentiate x2 dot, you actually get C double dot. So when you look at the state variables, it is x3. So when you differentiate x3 dot, what you will get is C triple dot. Okay. So what is C triple dot? C triple dot is all the things here is C triple dot here, and we move everything to this side. So this is what happens here. So so when we transform it into this one, it will be x1 dot equals to x2, x2 dot equals to x3, and x3 dot equals to minus 24x1 minus 24x1 minus 24x2 minus 9x3 plus 24r, which is from the previous slide. Okay, so why the output is, if you can see here, the output is CS, right? So this is the output. So Y here is equals to C, which is equals to X1. So then you are ready to transform it into the state space. Okay, so this is what you get in terms of state space form. So it is an A matrix. The A matrix is A 3 by 3. Okay, so obviously because we can know that because it is the state transfer function is in the S to the power of 3. All right. So next is you may be asked to draw the block diagram of the state space. All right. So this is how we draw the block diagram. What happens here is that you have S to the power of 3 here. You have x3 dot. Okay, the state space equate, the transfer function has S to the power of 3. So you have the C signal that is differentiated 3 times. Okay, the first differentiated and second differentiated. So what happens here is that you know that x3 dot here is equals to x3 dot here is equals to c triple dot, right? So c triple dot. So what we need to do is we need to integrate it, integrate once, integrate 3 times, first, second, and third, in order for us to get, the first integration, we get c dot, c double dot. The second integration, we get c dot, and the last one, we get c. So c is equals to the output, yt. So this is what happens here. Okay. So next is we have the summing point. 24R is the numerator. Okay, the R signal is multiplied by again which is 24, which is added here. And what is the minus here? The minus here is what happens down here is we look at x triple dot equals to minus 24 x1 minus 26 x2 minus 9 x3 plus 24R. So the signal from x3 is multiplied by 9, and it is connected to the summing point, and there is a minus form here. And similarly, the signal of 26x2 here, okay, so we tap the signal here from x2, and it is amplified by 26 gain 26, and the signal is connected to the summing point, and it is a minus. So lastly, the signal of 9 from x1, which is minus 24 x1. So the signal from x1 is amplified by 24, and it is connected to the summing point, and it is minus. So this is what happens here. So you get the output. All right. So next, in a case that we have this one, this case is the numerator is a constant. Okay, there are cases that the numerator is not constant, but instead it is a polynomial. Okay, so how do we do? So if the numerator is polynomial, so the first thing is we split the block diagram into two. So we have split it into one transfer function, which has a constant polynomial numerator, and also the polynomial, we put it in the second block diagram. So the two block diagrams will be cascaded. Okay, so if you can see here, there is an output signal x1 that is connecting the first block diagram to the second block diagram. So how do we solve for these questions? So what do we do is we have to do it one by one. So the first one is the output ys is equals to cs here, which is equals to the b times with x1. So in this is the S domain, and we transform it into time domain, which is we will get the constant b2 times with d2, the differentiation of x1, double differentiation, plus b1, double differentiation of x1 plus b0 x1. So then we will get the yt, the real yt signal, which is x1, x2, x3. So this is the general form. So let's proceed to the previous example. Now in the case that we have the numerator, a polynomial at the numerator. So the first step is we split the block diagram into two. So we have G1S here and G2S here. So we have solved for this one, for the first one, right? So in the first case. So now what we need to do, we need to solve for the second case, but we have to look again what are the state variables that we have already defined. So what we have defined in the previous example is that our x1 is equals to c, x2 is equals to c dot, and x3 is equals to c double dot. Right? So what do we do here? Okay, first is C is equals to, C equals to the transfer function here multiplied by x1. So next is we transform it into the time domain. So C is equals to x1 double dot, which because of s to the power of 2, and 7 x1 dot because s and 2 x1. So next is, you know that C is actually the output, which is y. So y equals to ct, which is equals to x3. And we know that the state variables that we have already defined is x1 equals to c, x2 equals to c dot, x3 equals to c double dot, right? So what happens here is that, x1 double dot here is equals to x1 double dot here is equals to x3. Okay, so it's equals to x3, which is the state variables that we have defined, and x1 dot here is equals to x2, and 2x1 here is equals to x1. Okay, so then we are ready to put it into a state space equation, which is y equals to, this is our state variables, and this is the the, the constants. Okay, all right. So similarly, next, what happens to the block diagram, the first variable form? So this is from the numerator, the denominator. So what happens when we have a polynomial at the numerator? It will become like this. The upper part here, which is y equals to y equals to x3 plus 7x2 plus 2x1. So, which is x3 plus 7x2 plus 2x1. Okay, so just take time to follow it back, then you get the whole things. Okay, so now I think we are ready for the skill assessment. So find the state equations and output equation for the first variable representation of the transfer function. So we have the transfer function gs equals to 2s plus 1, s squared plus 7s plus 9. So in a block diagram, in an open loop, what it means here is that we have a system, we have gs here, which is 2s plus 1 over s squared plus 7s plus 9. So we have the input here rs, and we have the output here cs. Okay, so the first step is we define state variable. Okay, so the state variables here is, let's define it as x1 equals to c, x2 equals to c dot. Since we have s to the power of 2, we know that we're going to have two state variables, which is x1, x2. Okay, c and c dot. So the second step is we differentiate the state variables, right? So x1 will be s1 dot, which is equals to c dot. x2 dot will be equals to c double dot. Okay, so the next one is we map. The third steps is we map it into the equations. So what happens here is that x1 dot, we map into the transfer function or into the model. Okay, so what happens here is x1 dot is equals to c dot, which is equals to x2. All right, so x2 dot is equals to c double dot, which is equals to, okay, so we miss the first step here. Okay, so which is equals to this one, we have to cross multiply it. Okay, so this is actually CS over RS. So we cross multiply. So this is what we get. 2S plus 1 CS equals to S squared plus 7S plus 9. Sorry, 2S plus 1 RS, 7S plus 9 CS. Okay, so, and we know that the upper here is a polynomial. So we have to split actually the block diagram into two. 1 over S squared plus 7S plus 9. You have an input RS and you have an output here. So this one is 2S plus 1. You have one output here which is X1S and this one is CS. Okay. So for the first one is, you know that it will be S squared plus 7S plus 9 X1 S equals to RS. Okay, so this is what happens here. So we will transform it into C dot. It will be X1 double dot plus 7X1 dot plus 9X1. Okay, equals to RS. All right. So what you see here is that equals to RS. So back to here, back to this step. So what we are seeing here is we shift x1 dot, x1 double dot is actually equals to C. Okay, x1 double dot here, you know that x1 equals to C, x1 double dot is equals to C dot, x1 double dot equals to s1 dot equals to C dot. So you're gonna expect that if x1 double dot equals to C double dot, right? So here, what's happened is that we shift everything to this part, to this side. So you will get minus 7 x1 minus 9 x1 dot plus R plus R. Okay, this is not RS because this is already in the time domain. So it is actually plus R. Okay, so then we are ready to put it into a state space. So this is what we get output here. So it will be x1 dot, x2 dot equals to some A matrix, and the state variables is x1, x2 plus with a B matrix, and we have the input RT. So x1 dot is equals to x2, x2 dot is equals to minus 7 x1, is equals to minus 9 x1 dot, sorry, yes, minus 9 x1 x1 minus 7 x2 plus with 1 R. Okay, so this is how you get to this answer. Okay, so the next step is, how do we solve for the numerator? Okay, so the numerator is, you know that how do we solve for the numerator? So the numerator is, you know that it is CS x1s is equals to 2s plus 1 multiplied by CS. So you know that it will be multiplied by CS, so it will be 2 C dot plus C. Okay, so the 2C, C is the output, right? So the 2C dot C dot here, so it means that look at the state variables. So you know that C dot is equals to x2, so it will become 2 x2, and the C is equals to x1. Okay, so which is equals to y. Okay, which is equals to the output. So the key point here is you have to keep the state variables. How do you formulate? You have to keep this one, the state variables here, in such a way that x1, x2, keep it into this form, which is as what we have defined in the state variables. And so your output will be 1 x1 plus 2 x2. So this is how you get to this answer. Okay, so that's how you get, those are the steps. Okay, so next one is we're going to learn, we are ready to learn how to transform the state space to a transfer function. So given the state and output equations, okay, in the general form, which is x dot equals to ax plus bu, b in times from input, and y equals to c times with the state variables plus with d in, times with input. So the first step is you have to transform the state equations into a transfer function, and we assume that there are 0 initial conditions. So what happens? The first for the state variables, it will be SXS equals to a matrix A times with the XS plus with the matrix B times with U, the input. So the output Y is equals to a matrix C times with XS and the matrix D plus with the matrix D times with U input. So since this is a B, C, and D are matrix, okay, so when we want to find, and we need to find the XS, okay, so what we need to do is we need to have some review back the matrix, how to solve a matrix equations. So in this case, to find S to find XS is we have an identity matrix minus with A, the matrix A, multiplied by XS and equals to BU. So the XS will be equals to an inverse of this identity matrix minus A times with BUS, which is the input. Okay, so given the system, the following system, find the transfer function, which is TS, which is equals to Y, the output, over the input, where the U is the input and Y is the output. So we need to transform these transfer functions, these state space equations, into a transfer function. So at the end, what we should get is YS over US, which is a transfer function, and this is the input signal US, and this is the output signal YS. So in the middle here is the transfer function. Okay, so the first steps is, first we analyze the equations. You know that this is the A matrix multiplied by with state variables plus with the B matrix multiplied by the input equals to the state variables that is differentiated. Okay, and the output Y here is the C matrix multiplied by the state variables. So the A matrix here is a matrix of, the size of the A matrix here is 3 by 3, right? So when we want to transform it into a transfer function, so since it is a 3 by 3 matrix, so our identity matrix here will be also, we also have to be 3 by 3. Okay, so a 3 by 3 identity matrix minus with the A matrix, then you will get the output here. Okay, so next is the inverse of this SI identity matrix minus A. So which is the rules is it is actually an adjacent of SI minus A over the determinant of SI minus A. So you need to revision back what is how to solve the adjacent matrix, which generally it will be we keep this and we multiply, find the determinant of this, which is then you will get S plus 3 minus 2. So which is S plus 3 plus 2. So this is how you get S squared plus 3S plus 2. So this is how you come up to this. So similarly, if you want to do for S plus 3, you have to keep this. So what happens here is 0 times S plus 3 minus 1. So you will get, it's supposed to be 1, right? So it's supposed to be 1 here. Okay, so yeah, you have to review back the adjacent matrix. Then next, this is the challenging part of the when you need to transform the state space into transfer function. Okay, so S plus 3. Okay, so lastly, you just have to, when you get the results, you just have to divide it with use the formula, which is the formula is TS, which is the formula is TS is equals to, sorry about that. The formula is TS is equals to YS minus YS over US, which is YF over US, which is equals to C multiplied by S I minus A and inverse of it, which is this one, times multiply with B matrix plus D. So substitute with the B matrix and D matrix and you will get this answer for 3 by 3 matrix. So for the second steps, which is to transform a state space into a transfer function, the challenging part is actually to solve the matrix equations. Well, I'm stuck here, but I hope you can revise back the matrix, the 3 by 3 matrix, how to find the inverse of the 3 by 3 matrix. Okay, so let's do the skill assessment together. So the skill assessment convert the state space equation to a transfer function. So you know that you have a state space equation, x dot equals to a matrix A, and the matrix A has the size of 2 by 2. The matrix B has the size of 1 by 2, if I'm not mistaken. And the matrix C has the size of 2 by 1. Okay, so what do we do first is we know that the transfer function TS is equals to YS, the output, over the input US, which is equals to C, the matrix C, multiplied by S identity matrix over A and inverse of it, multiplied by matrix B plus D. So let's find this first, all right? So the S multiplied by identity matrix minus A inverse 1 is equals to S0, 0S minus A minus 4 minus 1.5, 4 and 0. Okay, so you will get S plus 4, 1.5 minus 4 and S. Okay, so what we do next is we solve for the matrix. Okay, so in this case it is so Si minus A1, which is equals to an adjacent of Si minus A over the determinant of Si minus A. Okay, so the determinant is equals to S plus 4 minus 1.5 times 4, which is 6 minus 6. So the adjacent of it is, you have to move it, okay, the adjacent of it. So you have to find the adjacent of Si minus A. Okay, so then when you get the results, you just can multiply when substitute the value C, which is 1.5, 0.625, okay, multiply by the adjacent here, which is 1 over S squared plus 4S plus 6, some value here, adjacent, okay, multiply by B, 2, 0, plus D. In this case, the D is 0. So you should get your transfer function. Okay, so that's all. So at the end, you can self-check, do it and self-check that you should be able to get the transfer function is 3s plus 5 over s squared plus 4s plus 6. Okay, so that's all for this lecture. So I hope you understand it and thank you.